We should be live here. Good moment for Twitch. I think I know how to use a computer today. We have slides, we have picture. So that is good stuff. Today's February 5th, 2025 here at CSE598 at ASU. We just wrapped up doing format strings. We're moving on to our next topic here, which is like file struct hijacking and leveraging a different kind of weird machine to generate primitives. So that's our schedule here. This is our first module that runs for 2 weeks. I don't necessarily think it has to be a 2-week module, but it is possible to get kind of hard stuck on this one, as I'll point out a little bit later. So how are we doing so far as a course? There is not enough students for me to generate lots of pretty graphs. In this course, like I don't want to do that. It could de-anonymize people if you start comparing that. So instead, we'll just talk about the class as a whole. So we just wrapped up with format strings. As far as completion, the average student in the course solved 88% of the challenges in the module, which is awesome. That's good to see because I think my demo was kind of all over the place last week. So you guys figured it out. Hopefully the pre-recorded videos were more coherent than what I did last week. With what's the word I'm thinking of? Checkpoint and mean extra credit. Class grade across the whole right now, on average, is a 90.4. So I think we're cruising at a decent rate there, which is good to see. Or that's class grade format strings. Course grade across everything we've done so far and completed, we're at an 87%. I'm totally happy with it. One thing worth mentioning, as I always do, like this happened in 466, you guys should be aware that tail end modules are going to be significantly more difficult than where we start, right? Kind of like how in 466, you guys may have gotten hit with microarch and then system exploitation, and then finals are happening and you're just like, hey, I don't really have the time. Same thing will happen here, all right? Just know that. And so if you are not posting memes, do so now so you can cash in on that if you need it. With that, one of the things I realized that I didn't do so far in this course is talk about memes. We didn't do a meme review. And that's a big bummer, all right? Because I am still a big fan of memes. The camera has gone rogue. All right, go on camera. You see me? Maybe. So one of the things that has definitely happened is we kind of have been revamping the appearance or cosmetics of the site. There's some things that are good, right? Change is always hard. And feedback is mixed all over the place, right? Some people really like it. Some people really don't like it. Personally, like there's some things that I have a hard time dealing with because I think I'm blind. I think I need new glasses. There's some things that make it harder for me to see, but I will fix that on my own. So in the near future, my pwn.college will probably look different than your pwn.college because I'm going to write like a user script that's going to read you the font because I legitimately have issues with it. But yeah, the old logo and belt served us well, and that was awesome. The belt still exists. You can still get belts, but we're not going to have this like belt-centric design. And some people do actually like new logo. I like it. Primitive. So the first module that we did was about primitives, right? We kind of threw this out here and said, hey, write all this crazy stuff, generate some primitives and just go. And it was really more of a programming challenge and a knowledge check on things that you knew in the past. And so what this first module boiled down to was that
Except for level 10.
Except for level 10?
With the file format, file struct.
No, but okay. No, but that one
didn't give us the hint.
That one still boiled down to this.
Yeah.
And I didn't need to give you the hint if you were reasonably skilled at like GDB.
Yeah.
True. So I just answered a question on the Discord earlier today, and it was about one of the dynamic allocator misuse levels. where they have this echo function, right? And they're like, hey, I can only echo things that are on the heap. And that's true, right? That is the design of that capability in the challenge. And my hint or comment was that the heap is shared by all actions within that process, right? In this case, it's a single thread, so we don't have to go down the whole Tcache multi-thread thing. And other activities, right? Other actions may allocate and free things on the heap unrelated to what you're doing, right? Just because you aren't the one that calls malloc and free doesn't mean there's not some libc function that's calling malloc and free. And that's actually, so you should have like some intuition that that can happen. Because that is what's happening with the file struct from that level 10. But that whole module boiled down to exactly this. And so depending upon how well you abstracted, it was either not easy, but like acceptable, or it was just pure pain. This was a comment I made that somebody is reiterating, and it is still true in this module and probably every module of this entire course. You guys have a ton of freedom in how you approach things because we are giving you these primitives. And that'll be true across this entire course. If you try hard enough, you can probably reduce everything in this course down to get a write primitive, somehow turn that into ROP. And that isn't because this course like forces you to do that. It's because that is the nature of exploitation, right? Well, once you have these powerful primitives, where you go is kind of up to you. Format strings, we had a couple memes. Playing a game of telephone because we're trying to look at ourselves. We print a pointer, we get our pointer, we've got some writes here. Not entirely sure.
I get it.
You get it?
Well, how the program goes, you give it the input and then it gives you input back, right?
Okay, so yeah.
So it's like the challenge is telling itself what to print.
Oh, okay, yeah. Because I pass the input in, then it passes it back to me, but because it's this, it actually tells me something different.
Yeah.
Aha. See, like I need to spend a bit more time looking at this memes channel. Right here, this is like a classic problem with the format strings, right? You have some format string that you're trying to find yourself or insert a value, but things aren't quite lining up, and you're trying to add padding, and then that shifts things, and things aren't aligned anymore, and it just becomes this giant rage quit thing. I brought up last week that the Pwn tools format string and format string payload are there. And some people like them, but most people don't. And the degree to which you use them is entirely up to you. Just looking at the Discord, I saw some people enjoyed it and some people really did not. Some people used half of it, right? Which is totally fair. I think in my example I threw up there, I used half as well. For the primitives module, we had to deal with the multi-threaded heap. And Jeff does not do a very good job of figuring out what's going on with the threaded TCAP. So we had to unfortunately use pwn debug. We are not dealing with multi-threaded heap right now, and so we will return to the glorious land of Jeff. You are free to use pwn debug, but I can't help you. So the module we're starting here is file structure hijacking. It runs for 2 weeks. The syllabus literally says that it's 7 days. I'm giving you, I think, 9 or 10 instead. The idea is you get 2 weekends to hit that checkpoint, and literally 7 puts it on like Friday or something silly.
Syllabus says it's when?
Syllabus says 1 week for the checkpoint, but I'm giving you more than 7 days.
Oh, okay.
So I'm giving you more. I'm just letting you know, like, I'm violating the syllabus, but it's in your favor, right? Be on board. It's due on the 18th. As far as people wondering, hey, what do I need to know? It's the same stuff you needed to know last time. Use GDB. What is the GOT? What is ROP? Et cetera, et cetera. Cool. Demo plans. These first several modules boil down to give me the primitives, and then there's something crazy, which is where we'll spend a lot of time. Some people said that they saw the pre-recorded lecture videos this time. Is that true?
Yes.
Yes? No. Yes. Slacking. I was on day one, man. Watch the pre-recorded stuff. It's fine. If everyone watched the pre-recorded stuff, I'd literally have nothing to do here. I wouldn't be able to fill 3 hours. Okay, so does anyone know what a file struct is, or what standard I/O is? If you watched the pre-recorded, you have some idea. Ever used it? Ever used fwrite? No? All right, we can go with that. Gotta love my. I moved everything into junk. All right, we'll have our classic do.c. I'm going to include standard io.h. Standard IO, like almost everything we've done in 466, we just called read, we just called write. And that works, but it's not very efficient. So if I steal my own slides here, one of the things that happens every time that you perform a syscall, remember you're transitioning from user land into the kernel, right? And that context switch takes some amount of time. And so if I need to repeatedly read stuff from a file, if I repeatedly call read, I'm going to repeatedly transition into the kernel, and it's going to be kind of slow. There, in my experience in CS, and this is going to be a non-academic opinion, the answer to like everything in computer science is either a hash table or like caching. Like that is the answer to almost every problem. It just is. And so the question is, how can we make this IO faster? This time it isn't a hash table, and it's not really caching, but it's kind of caching, right? We buffer. And the way that works is via this standard IO library. So if I int main, let's have some buff, make it 256. And I'm going to have this file thing. So the family of functions that we're going to be using here are not into, because they're not syscalls, they are library functions here, like fopen, fopen, fread, fwrite. And I think we dealt with this a little bit in 466 when we had the Python. There's someone that we were doing something with IO in Python, and stuff didn't write, right? It was because it was buffering. I don't remember what the challenge was. It race conditions?
There were many challenges, but I don't think just one. Or the buffer thing. It was more than one.
Well, where you would try and like read or write something and you wouldn't get it.
Yeah, I think the last module you helped an officer or something like that. I had to click the button.
Yeah. This is why, right? This is the underlying reason that hurt. I don't remember what it was. It wasn't writing like pipe buffer. It was stream buffer here. And so these family of functions, instead of working on raw file descriptors, we have this, where is it? This file thing. And we don't have to necessarily know right now, as a user of this, what this file is, right? It's just some struct, it's some magic thing that represents a file instead of a raw file descriptor. So let's read our man page here. Let's have our file f. It's going to equal fopen. And this looks a bit more like what you have with Python, right? Where what are my arguments here? It's just give me a path and then give me a mode. And if we look at the mode, this follows that same syntax of like, just give me R, give me W. We don't have these low-level C constants that we have to pass in, right? It's a bit more user-friendly looking interface. So let's make some file that we're going to open. What do we want to put there? My secret stuff. And it'll go into my file. All right. So we're going to open my file for reading. And that's great. Now I have this F file. Well, how do I read it? Well, very, very similar to how we have F open. We're going to have F read, F write. The signature here is a little bit different because we have a pointer to the buffer that we're going to write from. We have the file that we're referencing, similar to a file descriptor, but we have these other two things. We have size and we have nmem. And these values are somewhat important. The idea here is that you are reading some unit, right? This unit could be 8 bytes in size, and so that would be the size of a member. And this depends on your use case, right? Maybe I am reading some data ints, and so I never want to read half of an int, right? I always want to read in 4-byte increments. I have a whole bunch of ints, right? In that case, my size here would be 4, and then nmem is the number of members that I want to read. So if I were to pass 4 for my size, and I pass 2 for nmem, all right, a member is 4 bytes in size. I'm going to read 2 of them. I'm going to read 8 bytes is what I'm asking for. So we can F read into our buff. For our purposes, I believe all the challenges just keep it simple, where we say a member is 1 byte, and we're just going to read however many to keep it simple math. You don't have to do it that way, though. So let's read 10 bytes into our buff. Then we're going to use our good friend printf, and we're going to say buff is %s new line buff, which will probably yoink out some garbage since it's not going to be null terminated, but oh. So you gotta read your man pages, man. This doesn't return a file, it returns a file star. And so, as will happen every stream. Okay. And so we are able to read in the first 10 bytes into that buffer on the stack and then just print it out with printf. And so now you're like, all right, well, that's super cool. Right? I learned a ton, Robert. Well, let's copy my do.c. We're going to have buffer.c. This is a rip of what I do in the first lecture video, but it's worth showing, I suppose. If instead of opening my file, we open something that is just infinite in size, like dev, I think we dev u random. On the right-hand side, we'll do it the way that we've done it in the past. Is that right? No, it's RD. Read into buff from 0 into buff. And let's read 56. And let's do this. I read from FD. See if I can write acceptable. What we're just going to do is we're just going to read a bajillion times here. And we'll do the same thing over here with fread. In both cases, we're going to read 256 bytes. In both cases, we're going to do it 10,000 times. Assuming I wrote acceptable C. These will both compile. The answer is no. You'd think, no.
You just need FC.
The header. I miss when compilers just warned me about those things, and they did the work, right?
Sometimes they do still. Like I can get printf without standard I don't know what the
Did you mean fread? No, I did not. Why do you think I mean fread? You're mad at me for that? There we go. All right. If I run these, that was pretty fast. Am I still way too fast? Oh, I need to make these two different binaries, don't I? Buffered that out. Not buffered that out. Oh, that was still pretty fast. Okay. So I just need to do more I/O to amplify this. How many? 1, 2, 3, 1, 2, 3, 4, 7. 1, 2, 3, 4. 1, 2, 3, 7 and 7. Buffered. Not buffered. All right. What have I done? Is this devu random? Well, that makes buffered look horrible. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. Okay, let's remove the randomness out of Hisk and just read null bytes. All right. Okay, so it was devu random that was getting here. Now we're literally just reading a ridiculous number of null bytes. And you agree the first time it was like what's happening?
But like, why would null writes be so much slower than reading random?
So dev random I could just block because dev random feeds from true random from system, right?
Oh, so you think it's blocking?
Yeah. So you random
Why would this one?
you random. So you random is pseudo random,
Yeah.
but it still requires some amount of entropy from the system itself. And so if I was at reading u random that much, which honestly that's quite a bit of u random, the pseudo random could just be like, no, we don't have enough entropy.
So you think it's not blocking, but just like returning an error?
I think it's blocking.
If it's blocking, then wouldn't it never finish?
Well, it can get enough. It can gain entropy over time. right? So like if you cat just dev random, this is unrelated to file structs for the record. You can, if I remember right, run out. Sure, system.
This is true random, right?
No, that's dev random.
No, like true random number, right? This is not pseudo random.
Yeah. The difference between dev random and u random is whether it's pseudo or not. If I remember right from the main page. I don't think there's any real random. No, there is real random.
What's real random?
So real random. I have to remember where they source it from, but it's from hardware stuff. Is where the kernel gets it from. It's hiding in a man page somewhere. Someone is welcome to correct me there, but that is my understanding of the difference between the two. And you can block on random. I'm surprised that Dojo would do that, but where just reading dev null, there's nothing going on the other side, right? The answer is always 0. And so I've eliminated the other side of that. And now this is a repeatable thing, which is what one would expect from a demo, where this is taking like 0.3 seconds and this is taking roughly 5 to 6, right? And the delay there is in how many times are we going into the kernel. And so when we use these standard IO buffered functions, what's happening is when we call fopen, we make this file. In the implementation here, they are mallocing a region of memory that is going to be like a buffer, and it's going to read ahead. So when I call fread here and I say, hey, I only need 256 bytes, this buffer is going to be, I'm going to make this up, hex 1000 bytes in size. It's going to be significantly bigger. And even though I'm only asking for 256 bytes, it will read ahead, and it will actually put more than 256 bytes into its internal buffer. So then the next time that I call fread, it doesn't have to go all the way out to the kernel and read from the file on disk. Instead, it says, hey, I still have some stuff that I think you might need. All right, I thought you might need this in the future. I already have it chilling on the heap. Here you go. Here's that data. And so that is the advantage of using fread. Fwrite is a buffered write. What this means is that when I call write, it doesn't necessarily go to disk. Instead, just like here we have a region of memory on the heap, we have a region of memory on the heap, and you say, hey, I want to write this to the file. Fwrite says, cool, I'm going to store it on the heap here for later because that's not enough for me to care, right? And it just does that until you fill that buffer on the heap. Once you filled that buffer, it flushes out and writes it out to disk. Now, a natural thing that you may think about, let's see if I can show that. Not the planned demo. There was a planned demo, but why would you do a planned demo? So, I'm going to write 10 bytes of this buff. Let's make this buff. Can I do this? I think I can do this. Or world. What do I need for? It is just. All right, I'm going to remove my file. I don't know if this will work or not. I think it. We'll compiler do.c. We'll run it. And we will immediately segfault. Why? Probably because you don't write this.
Look after it has the.
Oh, wait. It's because
Sorry, did I take the file player first?
F right,
Or
buffer size, nmem stream. I blame this guy here. I'm missing. Turns out you should probably open your file for writing if you want to write to it.
Oh.
If you didn't catch that, I did F open read and then tried to write. So let's make sure I don't have my file. Let's a dot out. Let's ls my file. Oh, it does exist, but it doesn't have anything, right? And that's because we called fwrite, and now it's sleeping. And fwrite said, "Yeah, we'll get to it later." Right? The hello world is sitting in this buffer memory that's on the heap, because it's like, well, if you want to write more stuff later, we'll wait until you have a lot more data to write it out. Now, once this 100 seconds is over and the challenge exits, we should be able to cat my file and see that content. Because what if what if I don't fill that buffer? It's 100 seconds, just way longer than I thought.
It's over a minute.
It is over a minute. Yeah, it seemed like a reasonable number when I typed it. Now I'm getting worried. Where are you? Oh, okay. It did in fact happen. It just felt like forever up here. All right. So I didn't for the record touch my file. So hopefully we do see we don't see the full hello world because I said I only wanted to write I think 10 bytes. But we get the hello world right there. Since I didn't put a new line, it gets to hang out over there on the left-hand side. But we hopefully I've reasonably proven to you that this is a buffered read and buffered write. And so the next question is, okay, well, this isn't a class about buffering, right? This is a security class. So why does this thing matter for this course? The answer is in the implementation of this buffer. To steal my own slides, if we think about how this thing works, now we have to think about what is that file struct, right? Instead of it just being, yeah, I don't know, it's this file thing. It's instead of a file descriptor, we just have this file thing and we pass it around. We have to think about this actual structure and what is it? How could it possibly work? And I blew away. That's all right. I didn't leave the one I wanted to open. If we look at libc, this is 231, which is the same version as what's running on the dojo. We can see what this structure is, and there's a lot going on, right? The way that it works, though, is we still just have some region of the memory where we're reading bytes into, and we're storing them to either flush them out, or we're reading bytes into to then pass them to user land later, right? And so in the implementation of this, there's all of these pointers. There's a read pointer, a read end pointer, read base pointer. There's pointers all over the place. But a simple way of reasoning about it is, all right, there's just some buffer in memory. And in the pre-recorded slides, we go into what these pointers are. But honestly, it's not that critical. As long as you have this mental model of we have some place where we start, right? This is the start of the allocation on the heap. This is the end of the allocation on the heap. And when we read in stuff from a file into this buffer, we have unread bytes here. And the thing that the file struct needs to track is where is the current cursor, for lack of a better term, of the bytes that are in the buffer. We've read up to here, so next time read is called, we're going to consume the next n bytes. Writing works very similarly, except now, instead of tracking where are the next bytes to return to user land, we're tracking where is the next location to put bytes when somebody calls fwrite. And then once this reaches a critical level, this gets flushed out to disk. For completeness, you can have something open for read and write, at which point the pointers get messy, and I don't want to talk about it. But it certainly is possible. But we don't need to reason about that to kind of abuse this thing. So based on our understanding of these pointers here, there is some relationship between the beginning of the buffer, the end of the buffer, and this cursor that decides when this goes out to disk, right? And if we were to open up, we're not going to do it, but if we were to open up the source code for fread and fwrite, we could find what has to be the relationship here, right? Like, clearly, if the write pointer reaches the end of the buffer and we want to write again, we have to clear this and reset back to the beginning. And so what we're going to do is we're going to take advantage of these pointers. Now, this is called file struct hijacking, and the first half of this module is kind of, I'll say that it's educational aim. We just give you a write. We just say, give me some bytes, and we're going to start writing at the beginning of this struct, right? And the reason we do that is because these are typically found on the heap, and we didn't want to have a dependence on you understanding where these things are located in the heap in order to corrupt. So we just give you from the get-go a write that starts at the beginning of this thing. And so what we can do is we can corrupt and clobber all of these pointers to create a scenario that will cause this to flush out. Yeah? Or read in. But remember, the buffer, right, as far as the implementation here, it just thinks this buffer is wherever these pointers say. And so it doesn't need to flush out from this region of memory that's on the heap. It can flush, all it knows is we flush out, like let's do, or we flush out from the bytes that we need to write out, right? And so it just knows wherever these pointers are is what drives where we start writing bytes from. So the early challenges here follow a pattern similar to this. It says clobber me, and then it's going to call read onto the location of the struct. And I don't know off the top of my head how big a file struct is. So we'll say 1,000 bytes. And then write it out. So if we build this thing, says clobber me, we give it something, and we're going to blow up, right? Because obviously what I just typed here immediately overwrote these pointers that are at the start of this thing. And what we need to do is be a little bit smarter about what are we corrupting and how do we make this make sense. Now you could look at this and figure out the size of all of this. This is okay. This is char star. That's 8 bytes. That's 8 bytes. That's 8 bytes. And do that on your own. This is one module where I think people do like the Pwn tools. Pwn tools help. Pwn tools has a, what do you call it? File pointer? Yeah. A file structure object as well. And what this is just a Python representation of that same struct, right? Because it's a known structure. And so we can interact with that. Over here, we'll take a quick look at it in IPython. From Pwn, import star. Very important that you type this one. Contact Arch, AMD64. You, for the record, no, I think I've made this mistake the past 2 years I've talked about it. If you don't have this, it'll look like it's behaving the right way, but you'll get a different file struct. And then you'll be like, why is everything exploding? So definitely make sure that you have that. And then you have f equals file structure. And if we look at this f, we see that, hey, this is the structure where we had the read pointer, read end, write out. It matches what we had in libc. Now, there's several ways to interact with this thing. You can call out the individual members, right, and set their value to be whatever you want. We just set that, right? So if there is some unique situation here that you want, you can set that up. Generally speaking, what you want to do, though, is you make this file structure, and then you call either fwrite or fread. And what these do is they will set the pointers of this file structure to satisfy the constraints such that you just get an arbitrary read or you just get an arbitrary write. Now, there's a gotcha here that we'll see as we use this guy. You see if I say I want to read from 133, why am I quoting that? I want to read from 1337 and I want to read 10 bytes. We see that the function returns the bytes of the structure, right? But the other thing that it does is it changes the value of the structure. And it's worth noting that because there may be a scenario where you want to do this fwrite, but Pwn tools make some assumptions. One of the things that I said this kind of buffered reading and writing does is it still does call the underlying read or write, right? We're just doing it less. Well, one of the things that's inside the file structure is file number. This is a file descriptor. It's the file descriptor that is backing our file struct, right? And Pwn tools just makes assumptions about what file descriptor you want. And so if I do fread, we see the file descriptor is 1, and if we fwrite, we should see that it assumes that I want file descriptor 1. That is not necessarily always going to be the case. And so you should be aware that Pwn tools is helping you, but Pwn tools is also making some assumptions that can hurt you. So I have this clobber me guy, and let's say that instead of writing to my file, let's write to devnull. All right, so there's no way that I could get this printed out. Somebody says 206 bytes, 216 bytes. Somebody knows the size of a file struct. I could have checked in Python, but I wasn't that clever. All right. So how do we use this thing? Well, first off, we aren't writing a C file. We are writing. Oh, that's a rare day. I don't have a do.py. And that's going to get clobbered on the stream. So let's do it down here. All right. Do the same thing that we had here in IPython. Whenever P equals process. And I want to send the trust pwn tools all of the bytes that are fwrite. Actually, that's going to be wrong. I want. So one of the things that I do, this everyone hates, but I think it's very important, and I'm doing it right now. In the pre-recorded lecture videos, I use this terminology of writing from memory to file. All right, and then this is because we end up thinking backwards about what is reading and what is writing. All right, especially when we start talking about primitives. If I am writing from memory to a file, what kind of primitive is that?
Arbitrary.
It's an arbitrary read because I'm arbitrarily reading memory. But since I'm writing from memory, what function, fwrite or fread, is being called? Fwrite. So to get an arbitrary read, I actually need to call fwrite. And that's why I use this like backwards, very specific wording of things. And most people hate it, but that's the why. Similarly, like right now, as I'm thinking about it, I'm like, well, do I want an arbitrary write if I want to leak out apparently hello whoa world, right? If I want to leak out that value, do I want an arbitrary read or an arbitrary write? I want an arbitrary read. I want to read the memory by calling fwrite, which means in pwn tools, I need to use, we look here, fwrite writes it to standard out. So I call fwrite to get the arbitrary read, right? And that will trip people up. It trips me up every time. Now, I think I failed in compiling this because I did not. We gave it PIE. There, we have no PIE, so now this should be, a constant location we can reason about. We will start this up. We're going to put the address of. Why is that there? That should be. Start.
Let's keep it like a range. Let's change it to a Charleston.
Man. Is that gonna make life good?
Wait, what?
Okay, whatever.
Wait. Get rid of the ampersand. You're printing a pointer to the pointer.
I am printing.
In reference to the pointer.
I'm printing the address of the pointer. Oh, yeah. Okay. Yeah, because now it's a point. Yeah, it's not a character literal on the. Yeah. Okay. So you want.
Wait, what? Wait, maybe I'm wrong.
This happened to me before. This is the classic. Robert doesn't know how to put a value in the BSS. All right, just to show that I this was planned. Just to show I did plan this out. All right. I did spend a little bit of time dry running this. The problem was actually not this. So let's see if I named this right. Okay. Apparently, I do. Okay, yeah, that makes sense. If I put it here, then it would go to the BSS because the pointer's on this stack. It would go up to read only because it's not getting modified. I'm a believer. That right. start. We print the address buff. Print buff. Why? What have I done? Okay, I have a working example. Okay, that's the right. This one. Target memory. Good. Compilers, man, how do they work? Twitch can't save me today. That makes sense. Okay. This could be Dojo insanity. Let's use the blessed GCC. What did I call this? Okay, yeah. All right, it's Dojo insanity. I was dealing with this on the other side. There's just yeah. All right, we have a no PIE binary. We have this in the BSS at a constant address. That's really all we care about there. The magic and mysteries of GCC will have to be dealt with another day. So I want to arbitrarily read that string, which UDB tells me is at this address. We've done this already. So what I want to do is I want to read from 404040. Hey, I think we've done that one before. And how many bytes do I want to read? I don't know. Give me 20. And then we will p interactive. Right? That seems like a reasonable thing to do. Any believers? Any believers in chat? No. Right? And this is where the Pwn Tools is great, but you have to kind of get what's going on. Why is this thing blowing up? And that is where everyone now knows to watch the pre-recorded lecture videos because the answer is hidden deep in here. This one's a bit of a troll, though, because you can do this while learning about arbitrary reads and writes, right, as I just did. But the answer is actually the third video. Yeah. Did you encounter this problem?
I attempted the first challenge and I got confused.
Okay.
I'll do what it likes.
So, we talk about this in this lecture video because when I recorded these videos, I had more faith in Pwn Tools, right? I thought it would be smarter, but we just don't have the technology yet. So this file struct is a complicated beast, right? And really what we're trying to mess around with are these pointers up here. But there's a whole bunch of other stuff going on down below, right? Now, most of these members we can ignore, right? They'll just kind of work, but some of them, or at least one of them, is fairly important. Let's see if I can find it on here. Boom, it's up there at the top, the old lock. This lock value exists for synchronization purposes, right? So imagine that we have multiple threads that are calling fread or fwrite. Well, these pointers need to not be vulnerable to a race condition, right? We don't want to have multiple threads trying to move these pointers around because that would corrupt the data in our buffer, our little buffer that's chilling on the heap that we saw. And that would be a problem. And so in the implementation of fread and fwrite, would they have this lock property? And if we were to look at the Python for it, we would see that in the struct, the Python Pwn Tools is just like, cool, man, we'll make this lock 0, right? Well, this lock value is supposed to be a pointer. And so what's happening is we are null pointer dereferencing. This needs to be a pointer to where that lock is. We can think of a lock just like a semaphore for all intents and purposes, right? So it needs to just be a pointer to some valid region of memory that can read and write. And Pwn Tools, in its totally reasonable default values, says, yeah, we'll just make that pointer 0. And that's pain, right? So how can I get around this?
Don't the challenges print the log for you? Or do they not?
Does the challenge print the log for you? I don't know if the challenges themselves do, but what I just wrote doesn't.
Yeah, but because if it does, you could just grab it. But I don't think that would.
That'd be pretty nice of us if we did that. I think these challenges try, or at least the early ones, like try and want to help you learn, right? But I'm claiming that we can succeed from this, right? If I had the lock, I could point it there, right? There's two other things that I could do. Remember, the requirement is just that it's a valid read-write region of memory. There's one thing that is specific to this challenge and what we know, and there's one thing that is like a general, reasonable way of dealing with. Any takers?
You just need to point it to a region you can read or write.
I just need to point it to some of the reads and writes. Do I know anywhere the reads and writes?
The binary.
The binary, right? This thing is compiled with no PIE, so I should be able to point this to anywhere that is read-write inside this binary. That is the specific to this challenge answer. So read-write 4044. Hey, it didn't go read-only. So let's send it over here. We'll find out.
Scale 1, 2, 3.
It can't be 1, 2, 3 because it's got to be valid memory in the binary, right? So that's why I was looking at this.
Yeah, like hex 40, 1, 2, 3 as well.
Oh, I'm sorry. Hex 40, 1, 2, 3. Yeah, that should be good.
I think 1, 2, 3, 4. Then.
Okay, 40, 1, 2, 3, 4. All right.
You're not sending it.
You are correct. So now this time I'm calling fwrite and I'm kind of throwing away the value that it returns, right? So I'm using fwrite to transform the file structure in Python. And then I am modifying that transformed version by setting the lock. Now what I want to do here is you can call bytes on f, and that will give you the same thing, give me the byte representation of that file structure. Dang. We still sag faulted. It was a good dream. It was. Let me just check one more thing. Yeah, no love. Let's make sure that's where we're blowing up. Historically, that's where we blow up. RDI 0. Right inside. Fwrite. It's looking at the reference fwrite plus RDI plus A. Are you? Okay. Anyone have any other ideas before I go down that rabbit hole? So I could try and make the lock value a real value. The other thing I could do is I could just leave it whatever it was, right? It was probably happy how it was originally. And fwrite, we said, can return as just this byte string. So I could just not send the whole thing. I can do a partial overwrite of the file struct. And that should be a pathway to success. Oh, you know what I didn't do?
Context.
3 years running, baby. Okay, all right. Still seg fault?
You just paused that.
No. We're at seg fault. We're seg faulting, but we're seg faulting at 40 because I didn't do 40. So this is it's seg faulting on the lock, right? That's our value. We're trying to move one into RDI where RDI is the lock. So it's doing the seg fault that I claim we're fixing. Did I? Oh, it's because we need 40, 1, 2, 3 to get read write. We went to non-read write memory, right? Because we did 40, 1, 2, 3. And so we ended up in this region of memory, which is read executable, which is why it's seg faulted. Because I trusted you. So it should have been 40 somewhere in this region of memory. So let's fix that and prove out the 40 and then 3 numbers. 1, 2, 3. Yeah?
I think that's not it's too many.
There's too many? I can't count. I believe it. 40, 1, 2, 3.
So yeah, 40.
Oh, 40, 1, 2.
So you want
Yeah.
44 and then that would.
That'll work. I just need it to go somewhere in that page. There's lots of numbers I could have typed. Just not 1, 2, 3. Okay. Continue. Oh no. Why do we sig abort? Sad day. So it doesn't like that. But you can do this. All right. Now let's figure out where this lock is. We don't need to do it for our right here. We got our F. I'm going to set, it is underscore lock, yeah, F. Underscore lock will equal some signal value. Then when I take the bytes of F, I can split this on OX69 on that value, except I need to make it a byte. And then what I care about is the first half, and I want the length. So 136 bytes up until that lock is encountered. So let's send the first 136 bytes instead and just let the lock be whatever the lock is. Let's just not make it our problem. So
You're sending the bytes after 136.
It's backward.
It should be colon 136.
see, this is why I need you guys. Because I'm barely functioning. Oh, it turns out if you learn Python, we can do this. Now, we could go into why that sig abort happened. My thought is that we pointed it to something that was non-zero, right? Because it is a lock. Actually, let's do that because I'm curious now. You okay with the rabbit hole? If we don't cut it early and we do write the lock,
Don't write
I do not write the lock. All right, I do write the lock to be, we said 40, 1, 2, 1, 2. Let's examine the giant hex at 40, 1, 2. Now, and what we see is it is not a null byte. And so if we think about how this lock works, it's going to be a 0 value when it's free, and then it's going to be a non-zero value when it's in use. And so we did pick somewhere that was read write, and odds are pretty good that it would be a null location. But in this case, we got unlucky, right? If instead, let's find somewhere that is null. 40, 40, 52. We still blow up. I don't know, man. Okay, but I'm telling you that that's how that thing works. But we don't need to do it for arbitrary read, arbitrary write. Okay, now we can do the same thing, except instead of calling this fwrite to write the standard out, performing an arbitrary read, we can use the same mechanism to say f dot read, and then the number of bytes that we want to perform an arbitrary write. In the interest of time, I'm going to yoink I think this one. Yes. Again, some trivialized thing here. The difference here is we're now calling fread inside the binary. And our goal here is to trigger you win by overriding some condition, which is just chilling up in the DSS, right? We'll build that thing. We'll grab the location of it. Forty, 40, 34. In this case, let's do a number like that. Let's avoid our lock problem. What was our magic number? 136? We blocked here. We told PwnTools we wanted to write 10 bytes.
Now it's expected.
So yeah, we want input. We're blocked on this fread, and the fread is looking for 30 bytes, and so I need to give it something here. And I still lose because today is not my
I think
day.
you need to give it more than 30. Like what you're giving it 10, so you might need to write more than.
So
Yeah.
now I win. Now, the reason for that has to do with that number and the number of bytes that we're trying to read in. Because what we're trying to cause here, when we want to read somewhere, is we want to prevent the scenario where read says I need to create a new buffer, right? I said that there's this buffer that's chilling on the heap, and that's where fread and fwrite store things. The size of this can be grown or shrank. And so if we create a scenario where fread or fwrite's like, hey, we need to have a bigger buffer because we're trying to read in, because what we're specifying here is the size, in the file struct, is the distance from the beginning of the buffer to the end of the buffer. And so when I had this at 10, the fread thought from here to here is about 10 bytes in size. But then the program said, I want to read in 30 units. This 30 units is bigger than that whole buffer. And so in the implementation of fread, it said, hey, our buffer is too small for the type of operations we're doing. And so even though we overwrote the pointer to the buffer, fread just said, we're going to throw that out. We need to malloc a new region of memory to use as a buffer, which is why I still said you lose. Does that make some sense? The TLDR is just make this number bigger than this number, and it'll play along nicely. If that's not the case, then in the standard IO implementation, it may malloc a new region of memory. Ooh, Honto dropping wisdom on us. I want to try the Honto wisdom. So Honto says, we don't have to do my crazy split this thing. Instead, we can do print the length of f string until, and then specify the member. 1, 2, 3, 1, 2, 3. That's a different, okay, so that's string until lock, so that's including the lock, right? Because that's a bigger number than what I ended up with.
So find the thing right before the lock.
Before the lock, unknown. Yes.
Okay.
The well-known member, unknown one. And that does get us there, right?
It's one of the well, we found. So we need unknown too.
Yeah. That is a cool trick, though. All right. So creating arbitrary reads and arbitrary writes here are pretty easy as long as we don't have to touch that lock, right? And it's not a whole lot of Python code. Now, the challenges here will make you think a little bit more about some of the other properties that are on there. I've loosely alluded to them already. Now, in my example here, I have this file that I'm opening here. What do you think standard in is? Standard out or standard error? Like we say that their file descriptors 0, 1, and 2, right? But they actually have a representation as a file like this. And that is part of why you can get buffered reading and buffered writing, because it doesn't make sense for standard in, standard out, and standard error to also be doing that kernel calling every time that you try and print something. And so some of these challenges, instead of using a kind of straw man file here, some of them will utilize this approach. Instead, the file that you're operating on may be standard out or standard in. That's going to make things a little bit messier, but the same general idea here apply. You just have to reason about, okay, what's happening now that I'm changing these properties of standard out or standard in. So this module, the first, I think, 6 challenges, do I remember right? Yes, the first 6 challenges, you should breeze right through them for the most part. All right, because there's going to be some permutation of that, what I just showed you. Level 7 is a historic brick wall for people. People do make it to the other side of it, but it is very common to be Honto regrets string until. He says he's looked at the source code and it's weird. That's what you get, man. I appreciate the tip, but it's crazy function. But level 7 now asks us to do something very different, right? It says to create a fate-wide data struct to hijack control of the virtual function. Okay, what? That this is no longer just like, let's do this arbitrary read or do this arbitrary write. And it's going to be not like a ton, but it's going to be considerably more lines in your exploit code. The good news about level 7 is once you get level 7, and understand what's going on there, a lot of the later stuff becomes considerably easy because they are adding constraints on this concept. Now, I'm going to take a break on time today, I think. So I'm going to start here because this is the rabbit hole of nonsense that we could definitely spend 3 hours on. So let's throw up our old logo. Soon I will fix it, and we'll be back in like 5 minutes or so. Okay, we're gonna go for it. Now, in the break, I did decide that I wanted to show that I do, in fact, understand what the lock is, and so we have it now. We just use the read instead of the write example here. You'll see that I'm sending the full file struct, but I'm setting the lock. Use GDB to find an address that is read write. That is null, happens to be the beginning of, I believe, the BSS. And if we fire off our do.py, now we're sending that full file struct, right? With the modified lock. We continue on down. Now it's blocked, waiting for bytes for the F read. We give it some bytes, and we see that you win. And so the requirement on the lock is, maybe we just got unlucky again, that it was a different value. Right? The requirement on the lock is that it points to read-write memory that is 0. Okay. And so this seems, as I said before the break, kind of straightforward, right? We're still just generating these primitives. This seems kind of easier than the printf stuff. And Pwn Tools does make it easy. I don't think it's worthwhile to like write this in C or deal with any other pain. Like that's how it works. In the pre-recorded stuff, we talk about the concepts and what the pointers, what the requirements are. And historically, I believe in the video, some of the slides are outdated or incorrect, but the live slides are. Years of people telling me like this pointer isn't quite right. Now, the crazy stuff happens here in this video. This is one of the longest videos that I have, for good reason. Because this is quite different than stuff that we've done before. This is closest to what we do with the heap, where we're like corrupting metadata or corrupting pointers. We're doing that same type of thing here. Now, that's one the reason that what we have here. We call this thing a file, right? I move fs debug b. All right. It's very similar to one of our examples, not anything crazy going on. All I really want is to have a file struct that we can poke at in GDB. Now for this, I need this GCC. All right. This is the type of like secret wisdom you only learn from pain. That was me for the first half of this day. No PIE, debug b dots. All right. So now if I GDB this, you will not have this problem because you don't have to compile things. And we start this, we disassemble main. I'm going to set a breakpoint at fwrite. All I'm really trying to do is get the address of the pointer, or of the file pointer. We'll break at main plus 396. We get there. The reason I'm breaking here is because I know calling conventions, and we looked at it in the man page, RCX here is going to be the pointer to that file struct. Now, GDB, if the stars align and you have libc debugging symbols, so on your local system, this is you're on your own. What we can do, you've probably seen syntax similar to this at some point from me. We can use the print command and cast RCX, which is that pointer, and say this is, I still didn't get it right, a file star, and then dereference it. And if you have libc symbols, you will not get that. If you do not have libc symbols, you will get this problem, which is what I thought I was going to not have. Okay. Do I have a good one in here? I swear I did this. Oh no, it's because I did struct file. File is yeah, it's a type def. IO file is the struct. Yeah, there we go. Okay. Okay, whatever. We'll use that one. It's the same. All I care about is that I can get to a file struct. So disassemble main. We'll break at main plus 396. We'll fire it off. I'm there. Now what we can do is we can cast this as a file, and then as a file pointer, and then dereference RCX. And if I did this correctly, and you can do this with any pointer, like you just saw me do with RSV. So this doesn't this won't tell you that this isn't a file struct. I am just taking the type that is a file struct and saying, pretend these bytes are a file struct and give me something pretty that looks like it. But in this case, I actually am casting a file struct pointer to a file struct pointer, which is nice. One of the kind of telltale things that'll help you know that it is actually a file struct is these flags values. The beginning of a file struct has this f bad, and then the least significant bytes are flags that mean a few different things. Pwn tools will set that for you. If you are trying to do it by hand, these flag values matter as far as whether or not the file is allowed to, for instance, read, write, those type of things. So I have this, and that's pretty cool, right? But this is kind of a lie because the file is outdated. We only need to know about the file as users of this thing. But the actual type of this struct is it doesn't have a type def or macro, is a struct IO file plus. And as you can see, the IO file plus is very different than the file. It's not. It's literally the exact same thing. It is a struct that consists of two members, the file that we already know, and then this Vtable pointer thing. Now, anyone? Oh, I'm not gonna ask. So the new thing here is this Vtable pointer, which is a virtual function table. And this is an optimization in how the standard IO functions work. Because what we have here, we can look at it. If I examine 20 giant hex at, now we could dereference that. I'm going to copy this and do it this way. But we'll see a virtual function table is just a bunch of function pointers, right? And these, if I were to grab one of these, see if I can do this right. Now, examine 10 instructions there. This is a pointer to IO file finish. And each one of these pointers are a pointer to some IO operation. Now, in the implementation of fgets, fwrite, fopen, all of these standard IO functions, they reference this virtual function table in their implementation to do sub operations. Right, so it's just it's a table that's full of function pointers, and what it allows is for dynamic resolution of these things that they need to do at runtime. Vtables are common in C++. This is not C++, but you'll find something very similar in C++ binaries. If you have an object, an instance of a class, and it needs to call a function, you end up having a pointer to a function table for that class that then tells you where the function is. Very, very similar concept. And so when like fread or fwrite needs to call something for these common operations, it will reference the file plus's Vtable pointer and then offsets from that base address to find the pointer for the function that it wants to call. Now, the kind of immediate thing that you'd think about is, all right, well, this is just kind of like the GOT, right? Why not just overwrite one of these? And when fwrite wants to call the Vtable plus, I guess, hex 38, instead of calling new file xs put n, whatever the heck that thing does, let's just put win there, right? That's something that you would think about doing. And at one point, you could do that. But you cannot do that anymore, right? That would be way too easy. Modern libc performs a like a sanity check of this region of memory and of this vtable pointer. We can see that. Where's the sanity check? That's my lock. Was that? Whatever, I linked to it already. Right here. When we validate the vtable, it has a like known region of memory, and like this must be here. And so we can't overwrite this vtable pointer. And this vtable pointer must point to a region of memory that is predefined. Now, another problem that I skipped back on the slides is our friend the lock, right? It's why the lock's on the third slide. The lock, or third set of lecture videos. The lock's here, and so we can read, write, and not care about it. But if we want to get all the way down to the vtable, we have to overwrite through this lock. And that is why you need to know that you can write the lock to any rewritable location that has a value of null, so that fread and fwrite can function. And so this is a problem that you have to deal with if we're going to start messing around with this vtable stuff. Because the idea is that we want to try and get fread or fwrite to call something that we control. But it has this validation going on. So the vtable pointer must point to the area in memory where the actual vtable is. And the vtable is actually quite large. Like if I were to, I did 20gx. That would be way cleaner if I said, there. Now you can see what they all are. These are all different function pointers, right? And that's too far. So there's not 200. But you can see that there's quite a few of them, right? And if I were to look earlier, there'd probably be function pointers there earlier as well. So if I can't overwrite and kind of influence what's going on here, how do I make this work for me? Well, it turns out inside of the vtable, there is a pointer, a function pointer, to IO W file over. And this sounds like, okay, this is like an obscure piece of wisdom, right? Why do I care about this particular function? 365 people, you know what this W stands for? Wide character. It's Unicode. We go back to dealing with data. All right. I love it. This is a Unicode. This is a function in the implementation of if I'm reading or writing wide characters or Unicode characters. And if I overflow this file, then I need to allocate a new region of memory, right? And so as part of calling this function, it will call doalloc buff. And you're like, okay, that's great. Why do I care about doalloc buff? Well, doalloc buff circles all the way back to our file structure. And instead of calling something related to this vtable that we started at, there is this wide data pointer. Wide data, again, Unicode. Oh no. Let's see if I can do this. Print this. RCX, Lloyd Star. Oh, I'd have to go file. Otherwise, I'd have to go file. There we go. Let's make that. Did you reference it? Nice. Okay. So this is the wide data structure. And the wide data structure, you see, it looks very similar to a file, right? You know what else this thing has? A Vtable. No, in the infinite wisdom of the implementers, we said that there's this sanity check of the Vtable of the file struct, right? We can't move this thing around too much. For whatever reason, and this may be changed in the most recent version of libc, this wide data Vtable does not perform that same validation. So somehow we need to get our F read or F write or whatever to call this function pointer, which then will call this, which will then reference this structure, which has a Vtable that we can control. And we have to set up all of these pointers to make this work and not explode. All right, which is why level 7 can be problematic, because there's a lot of time spent looking at these pointers and being like, what is going on here? Right. So the y data is essentially a file struct inside the file struct, and it has this Vtable pointer that we can overwrite. So our full strategy here, as I said, is we're going to kind of mess around with this Vtable pointer. We can't change it to wherever we want. We can change it within the bounds of this valid region of memory, right? So we can shift it 8 bytes or 16 bytes or so some amount, but it's only within the predefined region of memory that we could overflow and clobber this Vtable. But by doing so, by shifting that base address, let me find our Vtable. Let's examine 20 address, or 20 pointers from here. So envision that somewhere in fwrite, it calls, we have it on a slide. What is it? Plus 30, hex 38. I went and, so somewhere inside of the implementation of fwrite, it will call, or R15 is set to the base address of the Vtable. It will try and call the pointer that is stored at the base address of the Vtable plus hex 38, right? I don't list it. Okay, there we go. And it's supposed to be this new file XS put. Let's see if that's actually true here. Plus 38. It is. Oh, no, I got it wrong. Bam. There's our XS put in. We have it at the Vtable pointer. That's because I ignored these null bytes. But we see it right here. Now, what would happen if I incremented this by, say, 20 bytes? Then when it looks for XS put in, which is my third guy down here, I only shifted it by a little bit, right? But the base address plus, what is that? 16, 32, 48. Base address plus 48 now gets me to IO new file seek off. And this is such a minor shift that it's not going to get caught by that Vtable validation check. And so what we can do, even though we can't point the Vtable pointer wherever we want, is we can slightly shift the Vtable pointer to make the actions that fread and fwrite are doing resolve to a different function than what it originally intended. So let's see. This is the I don't know where it is in memory, so we will do some exploration together here. So envision that I have this R15 plus hex 38 that's going to be resolved, and I want to make it call IOW file overflow. Somewhere in here, Did I not? We'll just keep somewhere in this vtable is a pointer to that function, and we need to find it. Instead of doing this ahead of time, I was typing GCC. Just give me a bajillion. That's way past the vtable. Let's see if Honto saves me or not. I'm fine. I'm fine, Jones. That's too far. And I go behind it. I didn't see anything. All right, we have symbols. I wonder if I can just get GDB to just tell me where it is. Wouldn't that be the dream? Print IO W file. Over. That would have been too cool.
Stopped existing.
Oh, we're on the right version of libc. This thing exists. I just don't know why I don't see it. Hansa says he has no idea what's going on. He's not going to save me, and he is suffering from PTSD from this exact thing.
There's a symbol called _IO_W file jumps.
Oh, it's the underscore. There it is. Okay. That's the address of the function, but that is not the address of the pointer to the function, right? So you said you saw where
Underscore jumps instead of underscore overflow.
okay. Where is this in memory? Okay. And then what was my vtable? I just want to figure out where these things are, because they used to be reasonably next to each other. So why did I not see it? BE, BD. Okay, I didn't go far back enough. I should have gone back. I should just figure out what the distance is. Boop. Boop. 504. I didn't go far back enough. Yeah. All right. So if we were to take the vtable and subtract apparently exactly 540 bytes, then we get to this other vtable, right? There's this region memory that has a number of vtables, not just one vtable. And so what we're trying to do is we're trying to move the pointer to the files vtable back to the vtable for these wide characters. I was saved, not by you, Honto, but by glorious student. Now, if I were to set the vtable pointer to be exactly this, what function would be resolved when W file does this R15 plus hex 38? Hex 38 is going to be 1, 2, 3, right? That's going to be 0, 16, 32, 48, I'd end up with this, I believe, right? Am I mathing?
So that's the that access for that.
This is why computers were invented.
38 or 48?
Oh, you're right, 38. I'd be the excess put at. I can't do math, the computer can. And that isn't what I want, right? So I don't want to set it to the beginning of that vtable. I want to set it to be hex 38 behind the thing that I want to call. And the thing that I wanted to call, we said was right. I believe it's that one right there. The IOW file overflow. Just make sure. I don't think. There is IOW. Yeah, we'll go with that. So I wanted to call that one there. I need to go to this address minus hex 38. So I actually need to start a little bit behind there. Which is going to be zero, 8, 16, 32. So 620, hex 30. Yeah. So it would be this address right here. You agree? So it should be, if I got the right address, what'll happen is I can examine the address of what is my made up vtable here. We add that offset. No, I still can't math, man.
Minus 2 instead of minus 4. It was only like it's that's above the.
Did I grab the wrong? Oh, there's these zeros here. That's this one.
Plus a zero. It's confusing.
Yeah, no, gosh dang it. How many? I don't see the zeros. Yeah, there's two sets of zeros. Okay. All right. Let's let the computer do the math. All right, we'll print where it is minus hex 38. I want that address to be my vtable. In theory, it's easier if you can see it. But yeah. So I'm trying to figure out where I want this vtable to be so that when it resolves it and adds 38 and then calls the function, it's going to call this overflow. So now I have that. Once I have that, we said that it's going to, why did I exit GDB? Once I have overwritten the vtable to be that,
Yeah.
no, not RSP, RCX, because I don't want a file. I want a IO file. Plus. And it does need to be a struct. And okay. Once I have managed to set that vtable here, in the pre-recorded lecture videos, I stepped through it in GDB tirelessly, going through and finding how this ends up calling back into this wide data. instead of doing that live, let's just, that happens. All right. We set the vtable pointer so that it calls that IOW file overflow, which will then reference this pointer, which we control. Now, there's no restrictions on this wide data structure. So we could point this to the stack. You could point this to the VSS. We could point this to kind of wherever we want. In level 7, you have quite a bit of freedom as far as where in memory you can put that. We give you lots of space. And so you can say, all right, I'm going to have a wide data struct that lives here, right, at hex 1337 or whatever we give it. But if we were to look at, let's see if I can do this. File struct RCX. That's fine. And then we grab the vtable that exists. Can I get the address of it? Yes, I can. Which means I can set it equal to, oh, that wasn't the same constant. We did the math. Then I restarted GDB, so it's not going to be the same. No, it will. GDB will standardize it. Yeah. Where was my magic constant? This thing. Bam. What are you mad at? That work? Then we print a whole shebang. All right. So instead of just overwriting it, I'm just setting it in GDB. And what should hopefully happen here, if we continue, is we will segfault. And we'll be happy about it. All right. So we did segfault, and the question is, where did we segfault? In this case, we segfaulted in fclose. And if we were to examine, why is this a null? We are segfaulting. I'm not going to segfault where I want to. It successfully resolved to somewhere else. Gosh dang. This is why the pre-recorded lecture video is awesome, because I spent days stepping through this in GDB to find the exact spots to talk about. But it will call back to this wide data structure. In the wide data structure, we can set that pointer inside the file struct to be anywhere. And in the kind of like worst case, if we know the region of memory that we are overwriting, we can make this point to ourselves, right? Because the rest of this, we just consider to be like garbage, right? The way to start thinking about these pointers and these structures, instead of being like, I have a structure that is, I don't know, 80 bytes in size, you just care about a base pointer and an offset, right? And so when this wide data table or wide data member is accessed, we can make this pointer be anything as long as wide data plus whatever the distance is to the wide data vtable resolves to another valid address. But then this wide data vtable pointer is going to be offset to find the pointer to the function to actually call. It sounds crazy right now, but that's because I'm utterly failing to step through this in GDB.
It's like setting up dominoes.
It is. The correct way to make sure that you have all of them right is to perform the corruption, set your breakpoints in GDB, verify that these specific pointers are where you want, and that the pointer plus some offset is what you want. You don't have to care about having the whole structure available. You only care about the memory addresses that are actually being resolved in the assembly. Right? The concept of the structure is this high level C thing that doesn't actually matter. But in the assembly, it's just here's a pointer, we add something to it, and we dereference it. And if you start corrupting this stuff and step through it in GDB, you'll find where that pointer is used. You'll find the region of memory, you adjust it, you run forward, and you build through this. That's why level 7 takes most people a couple days. If you're a clever individual, you can watch me step through it in GDB correctly and draw conclusions from that, because that I stepped through a fully working one. I just don't show you the code. So you can see how these memory addresses resolve. With that said, 7, once you solve 7, you'll get through to 10 pretty quick because they are all permutations of hijacking this Vtable. And so your paying is definitely up there, getting the initial thing working. The difference between 7 through 10 is we give you less memory to play with, which is why I'm telling you, think about everything in terms of base pointers plus some offset, right? Instead of saying I need, I don't know, 136 bytes, and then I need this bytes. It doesn't matter, right? As long as it's valid, points to valid memory in the end, you're good to go. Level 11 onward, all use the same exact concept. It's just instead of giving you this arbitrary write at the beginning of the file, they have a kind of gamified setup here where you have a set of operations that you can perform. So I can reread to a node or write to a node. These are going to use fread, fwrite, things like that. And so instead of just giving you this arbitrary write at the beginning of the file, you'll have to do a little bit of finagling to make it work. Just to make sure that you understand when I perform this write to do the arbitrary read, what do I have to set up? But the kind of low level stuff that's going on there is still the same stuff that you did in the first half. So I have, what do I owe you? 1 more hour? So I can try and do the Vtable from scratch.
We'll just post them.
That's right. That's why the canned video for this one is money. All right. I know there was a question about one of the other challenges. Do you have anything that you need from me right now on stream? If not, we'll end it there, the 2-hour mark. Good? We're good? Honto is just forgetting this module exists. It is some pain, but the key takeaway there is just corrupting pointers, thinking about memory. We'll get there. You'll crush me on Friday. It'll be fun. All right. Goodbye. Good luck.